So we have learned even reactions for haloalkanes. Now we are going to learn even reactions for alcohols. The first even reaction what we are going to deal with is dehydration of alcohol. This is also called as acid catalyzed dehydration. So as the name suggests, we will be using acid as a catalyst over here. So we are going to take H2SO4, concentrated H2SO4 as a catalyst. Now let's understand how the reaction will take place with an example. So I have, let's say, CH3, CHOH, CH3. This is my alcohol. Now, if I take concentrated H2SO4, this concentrated H2SO4 can be written as H plus HSO4 minus. Now this H plus will go to OH first in the first step and will form a protonated alcohol. So the reaction of H plus with OH is an acid-base reaction. Acid-base reaction, and hence this step is going to be a fast step. So till now we have not started the elimination yet. Here just H plus has reacted with this OH, formed a protonated alcohol. Now this protonated alcohol will break its bond with carbon, forming a carbocation over there. So the product will be, so the intermediate would be CH3, CH plus CH3, and the removal of water will take place. So dehydration has taken place. Okay, dehydration, what we were expecting, dehydration has taken place, and we have got a carbocation. Now the formation of this carbocation is an RDS, or you can say it is a slow step. Now after this, what is going to happen? If there is a chance of rearrangement for this carbocation, rearrangement will happen. If there is no chance of rearrangement, attack of HSO4 minus will take place. Now one more important thing before I explain you the attack of HSO4 minus, that HSO4 minus is a better base than a nucleophile. So that means when it has a chance to behave like a base or a nucleophile, it will prefer behaving like a base, and that is the reason there will be no parallel SN1. So only even products will be formed. Fine. So here, as in the previous case when we were dealing with the haloalkanes, we had two parallel products forming. One is SN1 product, and another is even type of products. Now here we'll go properly through your even product will be formed. So now this HSO4 minus will attack on beta carbon. Now this is also my beta carbon, and this is also my beta carbon, and will try to remove the hydrogen from the adjacent position. Now both of these beta carbons are same, and hence the beta hydrogen will be same. So we can remove beta hydrogen from either of the positions. So I can write it as CH2H, CH, CH3. This hydrogen will get removed. HSO4 minus will take this H, forming CH2 double bond CH, single bond CH3. So this is my elimination product for an alcohol. Apart from that, what all we have to note in this kind of reaction? First of all, because this is an even reaction, we have already discussed for the even reactions that even reactions follow Sage-Zeff rule. Here also, when the reaction will take place, we will be following Sage-Zeff rule for forming the major product. In this specific case, we have the same carbons both sides, the molecule is symmetric, hence it really doesn't matter from where we are removing hydrogen, we will get the same product. But in other cases where the chain is not symmetric, you will be specifically following Sage-Zeff rule. So, Sage-Zeff rule is followed, and second, the reaction is going to be regioselective. Reaction is regioselective. Method and the reaction for even is same in the case of alcohols also. I'll just summarize it very quickly. We have taken an alcohol, we have treated it with concentrated H2SO4. From that H2SO4, H plus will first attack on OH, will make it a protonated alcohol. This protonated alcohol will detach from carbon, forming a carbocation. Then HSO4 minus will attack on the beta hydrogen, will take out that beta hydrogen and will form a alkene. This alkene will be formed using the Sage-Zeff rule. So major alkene will be the product of a Sage-Zeff rule, and reaction will be regioselective. When we are talking about HSO4 minus, HSO4 minus is a better base than a nucleophile, hence the reaction will go through only even. Apart from concentrated H2SO4, what other reagents we can use? One we already know, concentrated H2SO4 we can use, and the other reagent we can use is H3PO4. H3PO4 will also do the mechanism in the similar way and will give us the Sage-Zeff product as a major alkene. Okay, this is about our even reaction for alcohols. Now we'll see some more questions, more examples. I'll solve one or two questions for you. Rest you will solve on your own, and then we will discuss the answers. Now let's solve few more questions or few more examples for even of alcohols. Let's take the first example as, this is my OH, okay, this is a secondary alcohol. Now if this will be treated with H2SO4, the H plus out of it will first attack on OH, will form the protonated alcohol. Okay, and the removal of this H2O will be the next step, leading to the formation of a carbocation. Now this formation of a protonated alcohol is a fast step, whereas formation of a carbocation is an RDS. Okay, now once the carbocation has been formed, now we will see whether the rearrangement is possible or not. Here we do not require any rearrangement because the adjacent carbon is also a second degree carbon. So now we will look for the attack of HSO4 minus on the beta carbons, beta hydrogens. So this is my beta hydrogen, beta carbon, and this is my beta carbon. Let's mark them beta 1 and beta 2. So, and let's mention the hydrogen also over here. So this is hydrogen, and let's say this is also hydrogen. And if HSO4 minus attacks on beta 1 and removes this hydrogen from the beta 1 carbon, in that case the alkene formed would be this, right? Whereas if the hydrogen removal happens from beta 2, alkene form will be this. Now we had already discussed that the even reaction goes through Sage-Zeff mechanism, or you can say follows the Sage-Zeff rule, and hence will give the Sage-Zeff product as a major product. That means the removal of hydrogen will take place from the carbon which is more branched carbon, or more alkylated carbon, or more crowded carbon. So look at beta 1. Beta 1 is more crowded than beta 2. Beta 2 is a primary carbon, beta 1 is a secondary carbon. Hence, the alkene formed between beta 1 and the carbocation will be the one which will be the Sage-Zeff product. So this is our Sage-Zeff product. And this will be major. And this will be Hoffman product, and this will be minor. Here there will be no SN1 product formed, as we have already discussed that SN1 doesn't take place in the case of H2SO4, as HSO4 minus is the better base than a nucleophile. So reaction will proceed towards even reaction. We had already discussed what are two factors which can affect the reaction to reactivity towards SN1 or even. It is temperature and the behavior of the attacking reagent. If the temperature is higher, then also even is favored, and if the if our nucleophile or the base or the attacking reagent what we have taken here is more basic than nucleophilic, in that case the reaction will go towards the even rather than going through SN1. So even products would be major. Now let's take another example. This is my another alcohol. again, when I'll react it with concentrated H2SO4, H plus will attack on this oxygen, will form a protonated alcohol, giving me this. This water will get removed in the next step. So removal of water will take place, and we will get a cyclobutyl carbocation. As soon as we get a cyclobutyl carbocation, it should click in our mind that it will try to get a CPM stability, and hence it will rearrange itself in such a way that the ring contraction will happen and it will try to become CPM. So basically a new bond formation will happen between this carbon and this carbon, and bond will break between this carbon. So let's mark these carbons. This is 1, 2, 3 and 4. So a new bond will be formed between first carbon and the third carbon, and the bond between third carbon and fourth carbon will break, and this positive charge will shift to the fourth carbon. So the new rearranged structure will look like this. This is how the structure will look like. This is carbon number 1, this is 2, this is 3 and this is 4. Now after this, our HSO4 minus will attack on the beta carbon. What is the beta carbon over here? First carbon is the beta carbon, and will remove the hydrogen from this beta carbon, forming an alkene. So whatever the hydrogen was present over here will be removed by HSO4 minus and will give you alkene like this. You can't see the major product over here because this is the only product forming. So this will be the even product of this reaction. So both of the examples you have seen, the one example where rearrangement was not required, second example where we had done rearrangement. In the first example, we had two even products, one is major and one is minor. In second case, there was only one product and that was the major product. And these are two examples which will help you and understand the whole acid catalyzed reaction. Now I'll give you some questions. Try out those questions, write the answers in your notebooks, and then we will discuss how to solve them. I'll write down the questions, just copy them down.